In this video, we're going to examine the nature of functions. So often a scientist will conduct an experiment, develop their results with their inputs and their outputs, and then they'll plot a graph. And our problem here arises is just from the graph, it's very difficult to determine, well, what's the relationship between my input and output. Because the graph here, it could be a quadratic graph, but it could also be a cubic graph, or it could even be an exponential growth graph. So just by looking at the plot, we can't determine what the relationship is between my input and output. So this is the problem that we have. So before I explore the method, what I'm going to do is just give a quick revision of the main functions we've encountered so far in the module, the examples of where they occur, the typical curve, and their general equation. So you need to know all of these. There's the graph of linear functions and the general equation. Quadratic functions, cubic functions, and we can see there's a marked similarity between these graphs. We keep going. Reciprocal functions, general equation, typical graph, trigonometric functions, log functions, and their general equation. So from our 7 functions, we've only 6 so far, 1 more to go. You need to know the examples, what the graph looks like, and the general equation for each one. Exponential functions then is kind of split into 2. There's growth scenarios. There's the growth curve. And then there's the K scenarios. And the typical curve. Again, you need to be familiar with these, the curves, and the equations. The only significant difference between the 2 equations is the sign on the power. So, at the moment I'm just going to look at the general method, and then in the next video we're going to look at specific examples. So it's vital to remember those 3 slides. And in these problems we'll be given data, just like I showed you, and we need to determine, is it a linear, quadratic, cubic, reciprocal, log, or exponential function that we're looking at. And again, the words should help you. If we were looking at area versus radius, area is a quadratic relationship, so that should inform your thinking. If we were looking at, say, wind power versus wind speed, that's a cubic relationship. So this is why it's very important to be familiar with the examples outlined in the previous slides, because the choice you make determines the actions you're going to take, and whether you're going to achieve a successful outcome or not depends on your knowledge of those examples. So once you've decided, okay, I'm looking at an area, I think it's a quadratic relationship, you plot your variables. So if we think it's a quadratic relationship, we plot y versus x squared. Remember, on the table you're given x values and y values. Now what happens, what we're going to do, what I mean by plotting x squared, is you actually draw a new line on the table. So I'll just move the y values down a little bit, and here's the new line been inserted. So if you have your x values here, and our y values there, outputs, what we're going to do is square each x value, because it's a quadratic relationship. And now we're going to draw a graph with, we're going to ignore this and we're going to draw x squared along the bottom. 1, 4, 9, 16, etc. versus y. When we plot this new graph, and if we get a straight line, that verifies that y is proportional to x squared, which means the relationship between x and y is a quadratic. Conclusively, there's no doubt about it. So that's what I mean when I say plot y versus x squared. Similarly for cubic, plot y versus x cubed, reciprocal, y versus 1 over x, y versus log x for log, e to the power of x, or this easier version, which we'll explore later in the video. And as I said, if we get a straight line, this verifies that that particular function governs the relationship between our input and output variables. So we'll go through them all. Now, a linear function is a little bit of a trivial example because by definition a linear graph is a straight line. So here we're looking at the relationship between Fahrenheit and Celsius. Because it's a unit conversion, it's in the first list, we know this is a linear relationship. The power on C is 1. We've got a straight line. So there's no doubt about it. Just simply by the fact we've got a straight line means we're looking at a linear function. So it's kind of a trivial example to start us off. How do we know if our data is quadratic? Well, we could plot y versus x, and this is what I was saying, but this graph is not conclusive. Could be cubic, could be exponential growth, or it could be quadratic. How do we definitively determine which of those it is? Well, we plot y versus x squared, exactly as I just described. And if we get a straight line, that conclusively verifies a quadratic relationship exists between y and x. Similar for cubic, so it's the exact same process for each one. We could draw this, but there's no real benefit in drawing this graph because it's not conclusive and it takes ages. Whereas if we plot what we suspect, my input, I think it's a cubic relationship, so I'm going to cube my input and plot that versus y. And now if I get a straight line, that's a definitive result. There's no question about it. It's a cubic relationship that exists between y and x. How do we know if things are reciprocal? Again, a reciprocal curve could be exponential decay, could even be the left-hand side of a quadratic. But if we plot, so remember reciprocal, we suspect y is proportional to 1 over x, so that's what we actually plot. Determine 1 over x for each x value, and then plot that versus y. And if we get a straight line, then we've verified that that relationship does exist. So we'll be going over this in more detail, guys, in the next video. I'm just outlining the method initially. Same for logarithmic. Again, a log curve is fairly distinctive, but it's not definitive. Could be an inverse reciprocal. But if we draw the graph of y versus log x and we get a straight line, now we've definitively determined that a log relationship exists. Exponential is a little bit tricky because there's two types. So we could draw a curve again, y versus x. We could get the curve on the left, a growth curve, or a decay curve. But again, just by looking at the curve, it's not conclusive. So we could draw a graph of y versus e to the power of x. Now, unfortunately with this one, guys, is e to the power of x gets very big very quickly. If you start looking up e to the power 24, e to the power 36, the numbers grow extremely quickly. And it's difficult to kind of plot the graph. Your values get very, very big. You know, you could be up in, 10 to the power of 12 very quickly along your lower axes, and any kind of analysis then gets very difficult with this. So we take a little sidestep. We're trying to determine, is y proportional to e to the power of x? We could get the natural log of both sides. And now we'll have the natural log of y. The proportional sign acts the exact same as an equal sign. When we get the natural log of e to the power of x, we just have x. So this is the relationship we can explore. It's an awful lot easier because the natural log of most numbers is usually something very manageable, most often between 0 and 10. So if we plot this natural log of y versus x and we get a straight line, well, if we get a straight line, it verifies that this is true. If this is true, by definition, the line above it is also true. So to determine if something is exponential growth, we could plot the natural log of our y values. That would be our new line on the table. Get the natural log of the y values and plot those versus the original x values. Similarly, for exponential decay, we again get a straight line, but it would be heading downwards. So if you've got a positive slope and a straight line, that means you're looking at exponential growth. If you've got a straight line, linear straight line, and a negative slope, that means you're looking at an exponential decay relationship if you've plotted natural log of y versus x. So that, guys, is just an outline of the general method. In the next video, as I said, we'll explore the concepts in more detail. So thank you very much for watching.